There are two spacecraft out there right now, hurtling through space at roughly 35,000 miles per hour, that have been traveling since 1977, and they still haven't left the solar system. Let that settle for a second. These are the Voyager probes, Voyager 1 and Voyager 2, launched almost half a century ago. They have been flying continuously since before most people watching this were born. They've passed Jupiter, Saturn, Uranus, Neptune. They've crossed what scientists call the heliopause, the boundary where the sun's solar wind finally gives out, and they are still, by every meaningful definition, inside the solar system. Still inside. After 47 years, we put a man on the moon in 1969. We've sent probes to every planet in the solar system. We've landed rovers on Mars, dropped a probe into the atmosphere of Jupiter, and crashed a spacecraft into a comet on purpose, just to see what would happen. By any reasonable measure, humanity is a spacefaring civilization. And yet we have never once, not even close, escaped the solar system we were born in. That's the question tonight, isn't really, can we escape? Scientists aren't debating whether it's theoretically conceivable. The real question is why it's essentially impossible. Why the solar system, this place we casually point to on a diagram and think we understand, turns out to be one of the most effective prisons in the known universe. Not because of any single wall, not because of any one problem we haven't solved yet, but because of something more uncomfortable than that. Here's what most people picture when they think about the solar system. 8 planets, maybe some asteroids, Pluto out there on the edge, frozen and forgotten, and then stars. That picture is wrong. It's not even close to right. The solar system extends so far beyond what you're imagining that the distance from Earth to Neptune, a journey that took Voyager 2 12 years, is practically nothing by comparison. The real boundary of the solar system makes Neptune look like a neighbor across the street, and our fastest spacecraft, carrying the most sophisticated technology we've ever built, is crawling toward that boundary at a speed that makes the whole effort feel almost heartbreaking. Before we get into all of that, if you love digging into the deep end of space science the way we do here, take a second to like the video or subscribe to the channel. It genuinely helps more people find this kind of content, and it keeps us making it. Now let's get into it. Tonight we're going to look at the distances, the physics, the energy required, and the hard limits of what our civilization is actually capable of. Not the optimistic version, the real version. The one that makes the Voyager probes feel both miraculous and humbling at the same time. And by the time we're done tonight, you're going to understand exactly why. Let's begin by exploring your current understanding of where the solar system ends. If you're like most people, you picture it something like this. The sun in the middle, 8 planets arranged in a rough disk around it. Maybe an asteroid belt somewhere between Mars and Jupiter. Neptune sitting out at the far edge, cold and distant. And then, past Neptune, a little empty space, and then the stars. That's the mental image most of us carry around. It's clean. It's logical. It's what the diagrams in textbooks show you. It's also deeply wrong. The solar system doesn't end past Neptune. It doesn't end past Pluto. It doesn't end anywhere close to where you think it does. And once you understand where it actually ends, the whole conversation about escaping it becomes something entirely different, something much more uncomfortable. Here's the thing. A Astronomers and physicists understand that most people don't. The solar system isn't defined by where the planets stop orbiting. It's defined by where the sun's gravitational dominion stops. Those are two completely different boundaries, and the second one is so much farther out that they're not even in the same conversation. Think about what gravity actually does. The sun has so much mass that it bends space around it for an enormous distance in every direction. Not a flat disk, a sphere. Everything within that sphere, every rock, every chunk of ice, every cloud of gas, is gravitationally bound to the sun. It belongs to the solar system. When scientists say we haven't escaped the solar system, that's what they mean. We haven't left the sun's gravitational grip, and that grip extends far, far beyond anything you're picturing right now. So let's walk through what the solar system actually looks like. Because there isn't one edge, there are several, each one further than the last, each one representing a different kind of boundary. The first boundary most people have heard of is the heliopause. This is the point where the solar wind, a constant stream of charged particles blowing outward from the sun, finally gives out against the pressure of interstellar space. Inside the heliopause, you're inside a bubble of solar influence. The sun is actively shaping the environment around you. Outside it, you're in interstellar space, exposed to the broader galaxy. Voyager 1 crossed this boundary in 2012. That was a genuine milestone. The headline said it had entered interstellar space, and technically, that's true. But here's where things get uncomfortable. Crossing the heliopause doesn't mean you've left the solar system, not even close. The heliopause sits roughly 120 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the sun, about 93 million miles. So 120 AU sounds like a lot, and compared to anything in human experience, it is. But the sun's gravitational influence doesn't stop at 120 AU, it keeps going, and going, and going. Before the heliopause, there's another boundary worth knowing about, the termination shock, sitting around 85 to 100 AU out. This is where the solar wind starts to slow down, colliding with interstellar pressure and compressing. Between the termination shock and the heliopause, you have a turbulent region called the heliosheath. Voyager 1 crossed the termination shock around 2004, then spent 8 more years crossing the heliosheath before reaching the heliopause. 8 years of travel between just 2 of the solar system's boundaries. Think about that for a second. And even after all of that, after crossing the termination shock, the heliosheath, and the heliopause, you're still inside the solar system. Because none of those boundaries mark the true edge of the sun's gravitational reach. That distinction belongs to something much larger and much further out, the Oort Cloud. You've maybe heard the name. Most people haven't thought seriously about what it is. The Oort Cloud is a vast, roughly spherical shell of icy objects that surrounds the solar system at an almost incomprehensible distance. The inner edge begins around 2000 AU, maybe further. Let that sink in. The heliopause, the boundary Voyager crossed in 2012 after 35 years of travel, sits at about 120 AU. The outer edge of the Oort Cloud sits at 100,000 AU. That's more than 800 times further out. Everything inside the Oort Cloud is still gravitationally bound to the sun, still part of the solar system, by definition. The Oort Cloud is where long-period comets come from. Occasionally, a gravitational nudge from a passing star or the galactic tide perturbs one of these icy bodies, sending it tumbling inward on a long elliptical path toward the sun. We see those comets in our sky as visitors, but they're not from outside the solar system. They're from our own backyard. Just a very, very large backyard. We've never directly observed the Oort Cloud. It's too distant, and the objects within it are too small and dark to detect with current technology. But the evidence for it is strong, built from decades of studying cometary orbits and working backward to figure out where they had to originate. The math points clearly to a vast shell of material, still bound to the sun, extending nearly a quarter of the way to the nearest star, and it's still considered part of our solar system. This is the moment where most people's mental model of the solar system collapses. You thought the solar system was the planets, maybe a little extra space. The truth is that the solar system is an enormous layered gravitational structure extending in every direction for trillions of miles. What we've explored, every probe, every mission, everything we've ever launched, represents the innermost fraction of that structure. The solar system you've been picturing your entire life is a fraction of the actual thing. Here's a way to think about how big this problem actually is. Take a basketball. That's the sun. At that scale, Earth is roughly the size of a peppercorn, about 84 feet away from that basketball. Think about that for a second. 84 feet. You could walk that distance in under 30 seconds, and already most people's mental model of the solar system is blown apart, because when you picture the solar system in your head, you probably don't picture that much empty space between Earth and the sun. You picture something more compact, something more manageable. The reality is already uncomfortable, and we haven't even gotten started. At that same scale, Mars is another peppercorn sitting maybe 128 feet out. Jupiter swells up to roughly the size of a marble, but now you're standing about 435 feet away from your basketball sun. That's 1.5 football fields. You can barely see the basketball from there. Saturn is another marble, nearly a quarter mile out. Uranus and Neptune are small, bouncy ball-sized worlds sitting 1/2 mile and 3/4 mile away, respectively. Neptune is the last of the recognized planets, orbiting the sun at about 2.8 billion miles in real terms. That sounds enormous, and it is. But here's where it gets genuinely uncomfortable. Neptune is only 30 AU from the sun. An AU, an astronomical unit, is the distance from Earth to the sun, roughly 93 million miles. So Neptune is 30 of those. You might think that's the edge of the solar system, or somewhere close to it. It isn't, not remotely. The solar system doesn't end at Neptune. It doesn't end anywhere near Neptune. If Neptune is 3/4 mile from your basketball sun, the actual boundary of the solar system, the outer edge of the Oort Cloud, stretches out to roughly 15 miles in every direction. 15 miles. That's not a solar system. That's a region the size of a small city, and all 8 planets, including the ones we think of as the distant outer planets, are crammed into the first 3/4 mile of it. Let's step back from the analogy for a moment and just look at the structure itself, because it's worth understanding how the solar system is actually organized. Right at the center, you have the sun, which contains over 99% of all the mass in the entire solar system. Everything else, every planet, every moon, every asteroid, every comet, all of it combined, is less than 1% of what's here. Close to the sun, you have the 4 rocky inner planets, Mercury, Venus, Earth, and Mars. Then there's the asteroid belt, a region of rocky debris between Mars and Jupiter. Beyond that are the gas giants, Jupiter, Saturn, Uranus, and Neptune, all of them enormous compared to anything in the inner solar system. Past Neptune, things get less familiar. You enter the Kuiper Belt, a disk of icy objects extending from about 30 AU out to around 50 AU. Pluto lives here. So do hundreds of other icy bodies that most people have never heard of. The Kuiper Belt sounds like the frontier. It isn't. Beyond it lies a vast stretch of mostly empty space that's hard to even describe because there's so little out there that astronomers struggle to observe it directly. And then, surrounding all of it, is the Oort Cloud, a theoretical spherical shell of icy bodies beginning somewhere around 2000 AU, maybe farther. That's the real edge. That's where the sun's gravitational grip finally becomes too weak to hold things reliably in orbit. Now consider what that means in real distance. 100,000 AU is roughly 9.3 trillion miles. The sun's gravitational influence stretches nearly a quarter of the way to the nearest star. The solar system isn't a tidy little disk. It's an enormous sphere, and almost all of it is invisible, unmapped, and unexplored. Here's the part that should make you stop. Every human space mission ever flown, every probe, every rover, every crewed mission to the moon, every flyby of every planet has taken place within the first 50 AU of the solar system. Most of it has happened well within 5 AUU. The Apollo missions to the moon covered less than 1.3 light seconds of distance. That's not a figure of speech. Light takes 1.3 seconds to travel from Earth to the moon and back. Voyager 1, our farthest spacecraft, has been traveling since 1977 and is only around 160 AU out. In the basketball analogy, that barely registers. Voyager 1 hasn't even reached the halfway point between your basketball and the first houses on the next block, let alone the 15-mile boundary of the Oort Cloud. The entirety of human spaceflight history has taken place in a region that represents roughly 0.16% of the solar system's total extent, not 16%. Not 1.6% every Saturn V rocket ever launched, every Mars rover, every mission to Jupiter, all of it. The complete sum of everything our species has ever sent into space has barely scratched the surface of the structure we live inside. That's the thing that's hard to sit with. We celebrate the Voyager probes, and we should. They're extraordinary achievements, but when you put them in context, when you hold them up against the actual scale of the solar system, they look less like a bold leap toward the stars and more like someone stepping off their front porch and declaring they've left the neighborhood. Every spacecraft we've ever built, every mission we've ever launched, all of it has taken place in what amounts to the front yard. The real edge of the solar system isn't Neptune, and it isn't Pluto, and it isn't even the heliopause where the Voyager probes crossed into interstellar space. The real edge is something most people have never heard of. It's called the Oort Cloud, and once you understand what it actually is, the whole concept of escaping the solar system starts to look very different. Not difficult, not ambitious, effectively impossible. Here's what the Oort Cloud is. It's a vast spherical shell of icy bodies, chunks of rock and frozen material left over from the formation of the solar system. believed to surround the Sun at distances ranging from about 2,000 AU at its inner edge to somewhere around 100,000 AU at its outer boundary. 1 AU is the distance from Earth to the Sun, about 93 million miles. So when we say 100,000 AU, we're talking about 100,000 times that distance. That's roughly 9.3 trillion miles. And the Oort Cloud wraps around the entire solar system in every direction, forming a shell so enormous it makes the distance to Neptune look like the gap between your front door and the end of your driveway. Now here's the uncomfortable part. Nobody has ever directly seen the Oort Cloud. Not once. No telescope has resolved it. No spacecraft has reached it. Everything we know about it is inferred, pieced together from the behavior of long-period comets. When a comet swings into the inner solar system on a journey that takes thousands of years to complete, traveling on an elongated orbit that carries it out to enormous distances before pulling it back in, astronomers trace that orbit backward and figure out where it came from. Consistently, those origins point to a vast reservoir surrounding the solar system at exactly the distances we'd expect the Oort Cloud to occupy. The Oort Cloud is the only explanation that fits. What disturbs astronomers most isn't the Oort Cloud itself. It's what disturbs the Oort Cloud. Occasionally, the gravitational influence of a passing star or the tidal pull of the galaxy itself nudges one of those distant icy bodies out of its stable orbit. It falls inward, falling toward the Sun for thousands of years, eventually arriving in our sky as a comet with a tail millions of miles long. That comet made a journey so long that it was already falling when the Roman Empire was rising. It's still falling now, and when it finally swings around the Sun and heads back out, it won't return for tens of thousands of years. That's the scale we're dealing with. Now here's the fact that should genuinely stop you cold. The Oort Cloud doesn't just extend a little past the outer planets. At its outermost boundary, it reaches roughly 1/4 to halfway to the nearest star. Proxima Centauri is about 4.24 light-years away. The Oort Cloud extends somewhere between 1 and 2 light-years in all directions. So when you draw a line from Earth to the nearest star, you are still inside our own solar system for a significant fraction of that journey. The Oort Cloud is that big, and everything inside it, every single icy body, every chunk of frozen debris, is still gravitationally bound to the Sun. That's the definition of being part of the solar system. If the Sun owns your orbit, you haven't left. So what does it actually take to get through the Oort Cloud? This is where the numbers become genuinely difficult to process. Voyager 1 is our fastest spacecraft. It's been traveling since 1977. Right now, it's moving at roughly 35,000 miles per hour, which is faster than any object humanity has ever launched. At that speed, it will take approximately 300 years just to reach the inner edge of the Oort Cloud. Not to cross it, not to exit it, to arrive at the beginning of it. 300 years from now, Voyager 1 will finally be entering the part of the solar system we're talking about right now. And then, once it's inside, it faces a structure so enormous that crossing it will take roughly another 30,000 years. 30,000 years. Let that sit for a moment. Modern humans have existed for about 300,000 years. Agriculture is roughly 10,000 years old. The pyramids at Giza were built about 4,500 years ago. All of recorded civilization fits inside the last 5,000 years. and Voyager 1, moving at 35,000 miles per hour, will spend 6 times the entire length of recorded human history just crossing through a single structure that is still part of our solar system. That's not a journey, that's a geological timescale. It's a spacecraft the size of a small car running on nuclear batteries that are slowly dying, and it will drift through the outer reaches of our own solar system for longer than our civilization has existed, and nobody alive today, or for 1,000 generations, will be alive to see it exit. This is what makes the Oort Cloud so important to understand. It changes the entire framing of what escaping the solar system means. When people imagine that challenge, they picture getting past Neptune, getting past Pluto, crossing some invisible line into open space. But that's not escape. That's not even close to escape. Escape means clearing the Oort Cloud. It means getting past the last structure still bound by the sun's gravity. And that structure is so vast, so thick, so far away that no technology we have today, or that we could realistically build in the next century, could carry a human crew through it in a single lifetime, not even close. The Oort Cloud isn't a detail. It isn't a footnote in the story of solar system exploration. It's the main event. It's the reason the true edge of the solar system is almost incomprehensibly farther than anyone imagines. And the fact that we've never even seen it directly somehow makes it even more unsettling. This enormous invisible shell surrounding everything we've ever known, so far away that our best instruments can't resolve it, so massive that our fastest spacecraft won't reach its inner boundary for 3 more centuries. Voyager 1, our fastest spacecraft, will take about 30,000 years to pass through it, and that's if nothing goes wrong. In the summer of 1977, NASA launched 2 spacecraft that would become the most distant human-made objects in history. Voyager 1 and Voyager 2 lifted off within weeks of each other, both from Cape Canaveral, Florida. They weren't designed to escape the solar system. That was never the primary mission. They were built to study the outer planets, Jupiter, Saturn, Uranus, Neptune, and take advantage of a rare planetary alignment that wouldn't repeat for another 176 years. But the engineers were smart. They designed the trajectories to use each planet's gravity as a slingshot, stealing a small fraction of Jupiter's orbital momentum to fling the spacecraft outward faster than any rocket alone could manage. Without those gravitational assists, the Voyagers couldn't have reached the speeds they needed. They would have slowed, curved, and eventually fallen back toward the sun. The slingshots weren't a bonus. They were the whole plan, and it worked. Voyager 1 screened past Jupiter in 1979, past Saturn in 1980, and then kept going. It didn't stop. There was nothing left to stop it. Out past the planets, there's no atmosphere to create drag, no friction, nothing slowing it down. It just kept accelerating under gravity's diminishing pull and the momentum it had built up. By the mid-1980s, both probes were heading into the outer solar system at speeds that had never been achieved before, about 35,000 miles per hour, faster than anything humanity had ever built. And still, it wasn't fast enough, not even close. Here's where the timeline starts to feel uncomfortable. The outer boundary of the solar wind, the heliosphere, is called the termination shock. That's where the stream of particles flowing outward from the sun starts to slow down as it collides with the interstellar medium. Voyager 1 crossed that boundary around 2004, 27 years of travel just to reach the inner edge of the sun's wind bubble. Then came the heliopause, the actual outer boundary of the heliosphere, where solar wind stops entirely and true interstellar space begins. Voyager 1 crossed that line on August 25, 2012, 35 years after launch. That's the moment you may have seen reported as Voyager entering interstellar space, and technically, that's accurate. The probe is beyond the sun's plasma influence. It's in the space between the stars, except it isn't. Not really. Not by the definition that actually matters. Remember the Oort Cloud, that vast spherical shell of icy debris stretching out to 100,000 AU, still gravitationally bound to the sun. The heliopause sits at roughly 123 AU from the sun. The inner edge of the Oort Cloud starts somewhere around 2000 AU. Voyager 1 is still more than 1,800 AU short of that inner edge. It will take the probe approximately 300 years just to reach the beginning of the Oort Cloud, and then it will take another 30,000 years to pass through it. Think about that. 30,000 years. The Oort Cloud is so thick, so enormous, that our fastest spacecraft needs 3 times the length of all recorded human civilization just to cross it. Now multiply that against what the probe is actually carrying. A nuclear battery called a radioisotope thermoelectric generator. It converts heat from decaying plutonium into electricity. When the Voyagers launched, those batteries were producing about 470 watts of power. Today, they're down to roughly 40 watts. Less than the bulb in a bedside lamp. Engineers at NASA's Jet Propulsion Laboratory have been making brutal choices, shutting down heaters, switching off instruments one by one, trying to squeeze every last watt out of a machine that is nearly 50 years old and 15 billion miles away. They're not just dealing with dying hardware. They're managing it in real time across a communication delay of over 22 hours each way. Send a command, wait 22 hours for it to arrive, then wait another 22 hours for confirmation it worked. Every decision takes 2 days to verify, and yet the team keeps doing it because Voyager 1 is irreplaceable. There will never be another one. Not like this. The probe is expected to go dark entirely within the next few years. When the last instrument shuts off and the signal finally stops, Voyager 1 will still be drifting outward, silent, cold, but moving. It will reach the inner edge of the Oort Cloud around the year 2300. It will exit the far side of the Oort Cloud roughly 30,000 years from now. And if you somehow traced its path all the way to the nearest star, Proxima Centauri, it would arrive in approximately 40,000 years, give or take, assuming it were even headed in that direction, which it isn't. What Voyager 1 represents is simultaneously the greatest and most humbling achievement in human spaceflight. We built something that has survived for nearly half a century in the harshest environment imaginable. It still calls home. It still sends back data. Scientists are still learning from it. That's extraordinary. But set against the actual scale of escaping the solar system, it's like watching someone take one step toward the horizon and calling it a journey across the continent. The probe crossed the heliopause, yes, but the solar system didn't end there. The solar system ends at the Oort Cloud, and Voyager 1 has thousands of years of travel ahead of it before it even enters that region. We sent the fastest thing we've ever made, gave it the best trajectory we could design, used every planetary slingshot available, and kept it running for nearly 5 decades. It is, by every measure, the pinnacle of what our civilization has managed to throw outward into space. 47 years of travel, and the solar system still hasn't let go. The first problem is getting off Earth, and it's a bigger problem than it sounds. To leave Earth's surface and not come back, you need to hit a speed of 11.2 kilometers per second. That's about 25,000 miles per hour. Think about what that actually means. The fastest production car ever built tops out at around 300 miles per hour. You need to go roughly 83 times faster than that just to escape the planet you were born on, not to reach another star, not to cross the solar system, just to stop falling back down. That number, 11.2 kilometers per second, is called escape velocity. It's the minimum speed an object needs to break free from Earth's gravitational pull without any additional thrust. Below that threshold, gravity wins. You go up, you slow down, and you come back. Above it, you keep moving outward indefinitely. The math is derived from a relationship between kinetic energy and gravitational potential energy, and it doesn't care how clever your engineering is. You either hit the number or you don't. Now here's where most people stop thinking about it. They picture escaping Earth's gravity as the hard part. Get off the surface, clear the atmosphere, and you're free. But that's not how it works at all. Escaping Earth's gravity just means you've escaped Earth. You haven't escaped anything else. The Sun still has you, and the Sun is roughly 330,000 times more massive than Earth. At the distance Earth orbits the Sun, about 93 million miles out, the escape velocity from the Sun's gravitational field is approximately 42 kilometers per second. That's the speed you'd need to reach relative to the Sun to stop being gravitationally bound to it. To truly leave the solar system on a one-way trajectory with no return 42 kilometers per second, that's almost 4 times higher than what it takes to escape Earth. Here's where you get a small piece of good news. Earth is already moving. Our planet orbits the Sun at roughly 30 kilometers per second, and if you launch a spacecraft in the same direction Earth is traveling, you inherit that velocity for free. So in theory, you only need an additional 12 kilometers per second on top of what Earth's orbital motion already gives you. That closes the gap considerably. You still have to escape Earth's gravity first, and then pile on that additional 12 kilometers per second, but the math becomes slightly less punishing. Slightly. Not comfortably. Not easily. Slightly. To put 12 kilometers per second in perspective, the Saturn V rocket, the most powerful launch vehicle ever successfully flown, the machine that put humans on the moon, could accelerate its payload to roughly 7 kilometers per second in low Earth orbit. We're talking about the largest, most capable rocket in human history, and it didn't even get halfway to solar escape velocity relative to Earth's orbital frame. That's how steep this wall actually is. So how did Voyager 1 and Voyager 2 do it? Because they did. Both probes are on trajectories that will carry them out of the solar system, eventually over tens of thousands of years, as we covered earlier. But neither spacecraft left Earth with enough raw rocket power to reach solar escape velocity on its own. That's not a criticism of the engineers. It was deliberate. It was the only practical option they had. What the Voyager missions used instead was gravity assists. The probes were carefully targeted to fly close to Jupiter, and in doing so, they stole energy directly from Jupiter's orbital motion around the Sun. Jupiter is moving through space at about 13 kilometers per second, and when Voyager swung around it on a precise trajectory, the planet's gravity accelerated the probe and flung it outward. The spacecraft gained speed. Jupiter lost an immeasurably tiny fraction of its own orbital energy. so small it will never affect Jupiter's orbit in any meaningful way. But for a small spacecraft, it was enough. Without Jupiter, neither Voyager probe gets out. That's not an exaggeration. The gravitational assist was the mission. The rocket got them off Earth and pointed them in the right direction. Jupiter did the rest. Voyager 2 went further, using both Jupiter and Saturn for successive gravity assists, which is partly why it was able to continue on to Uranus and Neptune. Each planetary flyby added velocity that chemical propulsion alone could never have provided on any realistic fuel budget. And even with all of that, the raw power of some of the most capable rockets ever built, plus the gravitational energy of the solar system's largest planet, Voyager 1 is currently traveling at about 38,000 miles per hour relative to the Sun. That's fast. It's genuinely fast by any human standard. It also means it will take roughly 300 years to reach the inner boundary of the Oort Cloud, and another 30,000 years to clear the other side. So think about that sequence carefully. First, you need to escape Earth. That requires hitting 25,000 miles per hour at minimum. Then you need to escape the Sun, which requires reaching speeds that our most powerful rockets can't achieve, without help from the planets themselves. Then, once you've done all of that, you're facing an Oort cloud that is so vast it would take our fastest probe, already moving at 38,000 miles per hour, 30 millennia to cross. Each wall is bigger than the last. Each one requires more energy than the one before it, and none of them can be reasoned away or wished into irrelevance. They're physical realities, built into the structure of the solar system and the laws that govern it. Getting off Earth is hard. Getting away from the Sun is harder. Getting out of the solar system entirely is something else altogether. And that's just the beginning, because escaping the Sun's gravity is a completely separate challenge that makes leaving Earth look straightforward. There's a mathematical relationship at the heart of rocketry that makes everything harder than it looks, and once you understand it, you'll never think about space travel the same way. It's called the Tsiolkovsky rocket equation. You don't need to know the formula. What you need to understand is what it means, because what it means is genuinely alarming. The basic idea sounds simple enough. You want to move a spacecraft forward, so you throw mass out the back. That's all a rocket engine does. It throws mass, hot exhaust gas, out one end, and the spacecraft moves in the other direction. Simple, right? Here's where it gets uncomfortable. That propellant you're throwing out the back, it has mass, and before you can throw it out the back, you have to carry it. And carrying it means you need to accelerate it. And accelerating it requires more propellant, which also has mass, which also has to be accelerated, which requires even more propellant. You see where this goes. The relationship between the speed you want to reach and the fuel required to reach it isn't linear. It's exponential. That's the part that breaks people's intuition about rockets. Think about it this way. If you want to go twice as fast, you don't need twice as much fuel. You need dramatically more. And if you want to go 4 times as fast, you need exponentially more than that. The numbers spiral out of control almost immediately. This is why the Saturn V, the most powerful rocket ever launched, weighed about 6.5 million pounds at liftoff. The payload it delivered to the moon was around 100,000 pounds. The rest, roughly 96% of the entire vehicle, was propellant and the structure to hold it. And the moon is right next door, cosmically speaking. It's 250,000 miles away. Proxima Centauri is 25 trillion miles away. Now multiply that problem out. Here's where things get truly grim. Let's say you want to accelerate a spacecraft to 10% of the speed of light. That's about 67 million miles per hour. That's 40 times faster than anything we've ever built. Using the best chemical propellants available, the fuel-to-payload ratio you'd need is not 10 to 1 or 100 to 1. It's closer to 1,000,000 to 1. You'd need 1,000,000 pounds of fuel for every single pound of spacecraft. That's not an engineering challenge. That's a mathematical wall. No amount of clever design gets you around it, because the equation doesn't care how smart your engineers are. Let's make that feel real. Imagine you're driving from New York to Los Angeles. But instead of filling up at gas stations along the way, you have to carry every drop of fuel the trip will ever require, right from the start. And the car runs on itself. It burns its own body to generate power. So as you drive, the car gets lighter, which sounds helpful, except you started so heavy that most of your fuel is spent just moving the fuel. By the time you've burned through enough to actually start making real progress, you've consumed almost everything you had. That's rocketry. That's what every rocket ever built has been fighting against since day one. The situation gets even worse when you factor in deceleration. If you're trying to actually reach another star system, not just fly past it at full speed, but slow down and do something useful when you arrive, you need to carry fuel for braking too. Double the velocity budget and your fuel requirements don't double. They explode upward exponentially again. A spacecraft designed to travel to Proxima Centauri at 10% light speed and actually stop when it gets there would require fuel ratios so absurd they're almost impossible to express in terms that feel real. The numbers stop feeling like engineering and start feeling like fiction. And here's the part that makes this particularly brutal. We've known about this problem for over a century. Konstantin Tsiolkovsky worked out the math in 1903. Engineers have been staring at this equation ever since, looking for ways around it. Some have proposed staging. Break the rocket into sections. Drop each section when its fuel is spent, so you're not carrying dead weight. That helps. It's why every serious launch vehicle uses staging. But staging doesn't solve the exponential problem. It reduces it. It buys you a little room. It does not buy you the 1,000,000 to 1 fuel ratios you'd need for anything approaching interstellar speed. Others have proposed using the propellant more efficiently. Ion drives, for example, eject their propellant at much higher velocities than chemical rockets, which means you need less of it to achieve the same change in speed. That's real, and it matters within the solar system. But even ion drives, when you run the numbers for interstellar distances, fall catastrophically short. The efficiency gains don't come close to overcoming what the equation demands at the speeds we'd need. The honest truth is that the rocket equation isn't something we discovered and then worked around. It's something we discovered and have been losing to, slowly and quietly, for as long as we've been building rockets. Every mission in history has been a negotiation with this equation. How little payload can we get away with? How much fuel can we possibly carry? What tricks can we use to squeeze out a little more delta V? And for trips within the solar system, we've made those negotiations work. For escaping the solar system entirely, the negotiation breaks down completely. The equation simply says no. The rocket equation isn't an obstacle we can engineer around. It's baked into the physics of how the universe works. Let's talk about what we can actually do right now, because this is where things get genuinely uncomfortable. We've spent time talking about the rocket equation as a mathematical problem, but let's make it concrete. Let's look at the actual machines we've built, the actual speeds they've reached, and what those speeds mean when you hold them up against the scale of the solar system. Because the numbers are genuinely grim, and they don't leave a lot of room for optimism. Start with chemical rockets. Every launch vehicle ever built, the Saturn V that sent humans to the moon, the Falcon 9 that's become almost routine at this point. Every single rocket humanity has ever fired into the sky works on the same basic principle. You burn fuel and oxidizer together, and the exhaust shoots out the back. The physics of this limits you pretty severely. The best chemical rockets we've ever flown top out at around 25,000 miles per hour. That sounds fast. In any context you encounter in daily life, it is fast. But in cosmic terms, it's almost nothing. At 25,000 miles per hour, reaching Proxima Centauri, the nearest star, would take somewhere around 115,000 years. That's not a rounding error or a rough estimate. That's the actual number. The entire history of modern humans on Earth spans roughly 300,000 years. We'd be talking about a journey taking more than a third of that span just to reach the closest star. Chemical propulsion, the technology we've used for every crewed mission in history, is completely, fundamentally inadequate for escaping the solar system on any time scale that means anything. So what about ion drives? These are real. We've used them. The Dawn spacecraft used an ion drive to orbit both Vesta and Ceres in the asteroid belt. Deep Space One used one. They work by ionizing a gas, usually xenon, and accelerating those ions with electric fields. The efficiency is genuinely impressive. Ion drives extract far more speed per unit of fuel than any chemical engine can manage. But there's a brutal trade-off. The thrust is tiny. We're talking about the force of a sheet of paper resting on your hand. You're not blasting off with an ion drive. You're drifting, slowly building speed over months and years. That works fine inside the solar system, where you have time and relatively short distances. But the moment you try to apply that to escaping the solar system, the math collapses again. To reach even a minuscule percentage of light speed velocity, you'd need to operate an ion drive continuously for decades. And to power it at that scale, you'd need enormous reactors which add mass, which requires more thrust, and you're right back inside the rocket equation trap. Ion drives are not a path out. The problem is that every technological improvement we can imagine still runs headlong into the same fundamental constraints. We could design larger ion drives, extend their operational lifespans, or experiment with exotic propellants. We could pour tremendous resources into developing more efficient systems, but the underlying physics, the actual laws governing motion and energy, doesn't yield to engineering ambition. You're still constrained by the same equations, still fighting against the same universe. It's not a limitation we'll simply overcome through innovation or determination. This is where physics itself becomes the barrier, not human ingenuity. Now here's where people sometimes point to the Parker Solar Probe, and honestly, it's an impressive machine. Launched in 2018 to study the Sun, it reaches speeds of around 430,000 miles per hour at its closest approach to the Sun. That's the fastest any human-made object has ever traveled. New York to Los Angeles in about 6 seconds. Think about that for a moment. 6 seconds. And yet even at 430,000 miles per hour, the journey to Proxima Centauri would take approximately 6,700 years, not 6,700 months, years. More time than all of recorded human civilization has existed. The entire span from ancient Mesopotamia to right now isn't long enough for the Parker Solar Probe to reach the nearest star. But there's something even more uncomfortable buried in that number. The Parker Solar Probe doesn't actually travel at 430,000 miles per hour on its own power. It gets there by falling toward the sun and using solar gravity as a slingshot. It's not maintaining that speed. Out in interstellar space, far from the sun's gravitational pull, that trick disappears entirely. The probe would slow dramatically. The 6,700-year number assumes it somehow held that peak velocity forever. The real number would be far worse. That's the thing nobody really sits with long enough. Every impressive speed record in the history of spaceflight has come from either chemical explosions or gravitational assistance. We slingshot around planets. We fall toward the sun. We borrow orbital energy from Jupiter to fling ourselves outward. These are clever tricks, and the engineers who designed these trajectories deserve enormous credit. But tricks only get you so far. You can't slingshot your way out of the solar system in any reasonable time frame. There's no planet far enough out to provide the kind of gravitational assist that would meaningfully compress those timescales. The Voyager probes use Jupiter and Saturn beautifully, and they've been traveling for nearly 50 years and are still deep inside the Oort Cloud, with 30,000 years to go before they're fully clear. So take everything on this list and hold it together. Chemical rockets, ion drives, solar gravity assists, the fastest spacecraft ever built, every method, every trick, every record-setting mission. The best-case velocity we can achieve with current technology still leaves us facing journey times measured in thousands of years just to reach the nearest star. And the Oort Cloud, the actual gravitational edge of our own solar system, is closer than that. Every propulsion system humanity has ever built or flown would leave us stranded in the solar system for thousands upon thousands of years. So let's say we want to go faster, really faster, not just marginally better. We've already established that everything we currently fly is catastrophically slow. Chemical rockets, ion drives, the Parker Solar Probe doing its gravity trick near the sun. None of it comes close to what escaping the solar system actually requires. So the natural question is, what's next? What does the serious end of the propulsion spectrum actually look like? And here's where things get genuinely interesting and genuinely uncomfortable in equal measure. The first step up from chemical rockets is nuclear thermal propulsion. The concept is straightforward. Instead of burning fuel to generate heat, you run hydrogen through a nuclear reactor, superheat it to extreme temperatures, and expel it out the back as thrust. You're not burning anything. You're using the heat of nuclear fission to make your propellant move faster. This gives you roughly twice the efficiency of the best chemical rockets we've ever built. Twice as efficient sounds impressive, but twice as efficient as catastrophically inadequate still leaves you in deeply uncomfortable territory. You'd get to your destination in 50,000 years instead of 100,000. That's the ceiling. Nuclear thermal propulsion is a real technology. NASA tested reactors for it in the 1960s under a program called NERVA. The engines worked. They ran. But twice the efficiency of a chemical rocket does not get you to the Oort cloud in any time frame that means anything to a human being. So engineers and theorists have pushed further, much further. And that's where you arrive at Project Orion. Project Orion was a serious government-funded study that ran from the late 1950s into the 1960s. The concept was exactly as audacious as it sounds. You detonate nuclear bombs directly behind your spacecraft, one after another, hundreds per minute. A massive shock absorber plate on the back of the ship absorbs each blast, converting the explosive force into forward thrust. Computer simulations at the time suggested this could actually work. Properly designed, an Orion-type spacecraft could potentially reach several percent of the speed of light. Several percent. That's a number that starts to matter. At 5% light speed, you're talking about a journey to Proxima Centauri measured in decades, not millennia. This wasn't fantasy. Physicists like Freeman Dyson worked on it seriously and believed the physics was sound. But let's talk about what seriously studying it actually meant in practice. You'd need thousands of nuclear warheads, not stockpiled somewhere, detonated continuously directly behind a crewed spacecraft. The radiation exposure to the crew would be extreme. The engineering challenges of building a shock absorber plate capable of surviving thousands of nuclear detonations are enormous. And then there's the political reality. The 1963 Partial Test Ban Treaty effectively made it illegal to detonate nuclear weapons in space. Orion was shelved, not because the physics was wrong, but because the world decided, reasonably enough, that continuously exploding nuclear bombs in Earth's atmosphere or in orbit was not something any government was going to permit. The most promising propulsion concept of the 1960s died in a filing cabinet. So you push further still. You get to fusion. Fusion is what the sun runs on. Hydrogen atoms are forced together under extreme heat and pressure until they fuse into helium, releasing energy in the process. The energy output per unit of fuel is staggering, orders of magnitude beyond what chemical combustion produces, and significantly beyond fission as well. Hydrogen, the fuel required, is the most abundant element in the universe. An engine that ran on controlled fusion would be dramatically more efficient than anything we've ever built, and it would run on fuel you could theoretically collect from space itself. On paper, a fusion rocket is one of the most compelling propulsion concepts humanity has ever seriously considered. There's one problem: we haven't done it yet. Not in a power plant. Not in a laboratory. Not anywhere. Scientists and engineers have been attempting controlled nuclear fusion since the 1950s. 70 years of effort, billions of dollars, facilities like ITER in France that cost $20 billion just to construct. We've gotten closer. Recent experiments have achieved what's called ignition, a fusion reaction that briefly produced more energy than the lasers used to trigger it. That's a real milestone. But ignition in a laboratory environment, under extraordinarily specific conditions, is an enormous distance from a sustained, controllable fusion reactor that can power a city, let alone a compact engine that can power a spacecraft. Even the most optimistic projections from serious researchers put a working fusion power plant decades away. A fusion rocket, which has to be far smaller, far lighter, and capable of sustaining a directed thrust reaction rather than just generating electricity, is decades beyond that. We are talking about technology that might exist in the second half of this century if everything goes well. And things in fusion research have a long history of not going well on schedule. Think about that for a second. The most promising propulsion technology we can actually envision engineering, with a realistic path from here to there, is something that might be ready in 50 or 60 years if we're lucky. And when it's ready, it still won't get you out of the solar system in a human lifetime. Here's the genuinely uncomfortable part. Let's be generous. Let's say fusion works tomorrow. Someone flips a switch and we have a working compact fusion drive ready to bolt onto a spacecraft. What does that actually give us? Estimates vary, but a fusion rocket could realistically reach somewhere between 1 and 10% of the speed of light, depending on the design. At 1% light speed, the journey to the inner edge of the Oort Cloud alone would take centuries. At 10%, a figure that represents the absolute optimistic ceiling for fusion propulsion, you're still looking at generations of travel before you've cleared our own solar system's gravitational boundary. Even fusion, the most energetically promising concept we can actually envision building, would leave us crawling through the solar system at speeds that make the journey to the Oort Cloud a multi-generational undertaking. Antimatter is the most seductive idea in theoretical propulsion, and it's also the most brutally illustrative of how far we are from solving this problem. Here's why it's so appealing. When matter and antimatter collide, they annihilate each other completely. Not mostly, not efficiently, completely. Every single bit of mass converts directly into energy, with 100% efficiency. Compare that to fusion, where less than 1% of the fuel mass actually becomes energy. Compare it to chemical rockets, where the conversion is a tiny fraction of even that. Antimatter is, by a wide margin, the most energy-dense reaction that physics allows. There is nothing more powerful available to us within the laws of nature as we currently understand them. A relatively small amount of antimatter could, in theory, accelerate a spacecraft to a meaningful fraction of the speed of light. That's not speculation. The math works out. The energy is real. And that's exactly what makes the next part so grim. We have produced approximately 20 nanograms of antimatter in all of human history. 20 nanograms. A nanogram is a billionth of a gram. All of our particle accelerators, every major physics facility on the planet, running for decades. The total output is something you couldn't see with the naked eye. It wouldn't register on a kitchen scale. It wouldn't register on any scale you've ever encountered. And the cost of producing even that microscopic quantity runs into billions of dollars. Some estimates put the price of a single gram of antimatter at over $60 trillion. That's not a rounding error. That's not a figure that gets better with economies of scale. At current production rates, accumulating enough antimatter to actually fuel an interstellar mission would take longer than the current age of the universe. Think about that. The universe is roughly 14 billion years old. We'd need more time than that just to gather the fuel. And that's before we even talk about storage. Antimatter cannot touch ordinary matter, not even air, not the walls of a container. The moment it contacts anything made of normal atoms, it annihilates instantly and releases an enormous burst of energy. To store it, you need perfect magnetic containment, a system that suspends the antimatter in a vacuum, using powerful magnetic fields with zero failures for years or decades on end. One power fluctuation, one equipment malfunction, One unexpected failure in any component of that containment system, and your entire fuel supply detonates. The energy release from even a small quantity of antimatter would be comparable to a nuclear weapon. So you've got a fuel that's theoretically perfect, practically impossible to produce, catastrophically expensive, and which will destroy your spacecraft if you store it improperly for even a moment. That's where antimatter actually stands today. So let's turn to something that sounds a lot more achievable: solar sails. The concept is elegant. Light carries momentum. When photons strike a reflective surface, they transfer that momentum and produce a tiny push. If you construct a sail possessing adequate size and minimal weight, sunlight alone can accelerate it to significant speeds over time. It requires no fuel. It requires no combustion. It's been demonstrated in actual space missions. The Japanese spacecraft Icaros deployed a solar sail in 2010 and confirmed that light pressure was producing measurable acceleration. This technology is real. It works. The Breakthrough Starshot initiative, announced in 2016, takes this idea further. Instead of relying on sunlight, the proposal involves positioning an enormous laser installation on Earth and fire it at a tiny probe equipped with a lightweight sail. The probe would weigh about a gram. The sail would be a few meters across. The laser would accelerate it for a few minutes, and by the end of that burn, the probe would be traveling at roughly 20% the speed of light. At that velocity, it could reach Proxima Centauri in about 20 years. That sounds extraordinary. And the physics isn't wrong, but the engineering is where things start coming apart. The laser array required to pull this off would need to generate gigawatts of power. That's the output of a large power plant, all focused on a target the size of a postage stamp that is already accelerating away from you at thousands of kilometers per second. The precision required is almost incomprehensible. Any misalignment and the laser misses entirely. The sail has to remain perfectly oriented relative to the beam during the entire acceleration phase. One wobble and it's over. Then there's what you actually get at the other end. The probe carries no meaningful instruments, no significant power source, no communication array capable of transmitting data across 4 light years at any useful rate. You might receive a handful of images, a few basic measurements. That's your return on investment from a project of this scale. And the probe can't slow down. There's no mechanism to decelerate. It will scream past Proxima Centauri at 20% light speed, with perhaps a few hours to observe anything before it disappears into deep space forever. No orbit, no landing, no second look. Just a brief, high-speed flyby, and then silence. And this is the best-case version of solar sail technology. No humans, no stopping, no possibility of follow-up. Just a microchip hurtling through the void, transmitting a few images back across a gap so large that the signals take 4 years to arrive. Both of these ideas, antimatter and laser-pushed sails, represent the absolute edge of what human ingenuity has been able to conceive for getting out of the solar system. They're not fringe science. They're taken seriously by serious physicists, and even they fall short in ways that aren't fixable with more funding or more research time. These aren't engineering problems we're working through. They're physical and economic walls that no amount of optimism makes smaller. Even if we solved the fuel problem, even if we built the most efficient engine imaginable, we'd still hit something worse. This is where propulsion stops being the problem. Because there's a limit built into the universe itself, something that has nothing to do with engineering or funding or political will. It's the speed of light, and it doesn't care how clever you are. Here's what Einstein's special relativity actually tells us. Nothing with mass can reach the speed of light, not approach it and then push through, not get close enough that it doesn't matter, actually reach it. That's impossible. The reason is mathematical and brutal. As any object with mass accelerates, it gets harder to accelerate further. The energy required doesn't grow linearly. It climbs toward infinity as you approach light speed. You'd need infinite energy to hit 100% of the speed of light. That's not a number we can eventually produce. Infinite means never. So the speed of light isn't a wall you crash into. It's a ceiling that keeps rising the faster you go, always just out of reach, always requiring more than you have. Light travels at about 186,000 miles per second. That's roughly 670 million miles per hour. Our fastest spacecraft, the Parker Solar Probe at its absolute peak, hits around 430,000 miles per hour. That's about 0.064% of light speed. Think about that for a second. Our fastest achievement is not even 0.1% of the speed of light. The gap between where we are and where we'd need to be is almost incomprehensible. Now, some people hear this and think, okay, but what if we got to 50% of light speed? Or 90%? Wouldn't that still be fast enough? And here's where it gets genuinely strange, because relativity introduces something called time dilation. At relativistic speeds, time doesn't pass the same way for everyone. A crew traveling at 90% the speed of light would experience time passing more slowly than people back on Earth. At 99% of light speed, that effect becomes dramatic. For every year the crew ages, roughly 7 years would pass on Earth. Push to 99.9%, and the ratio is even more extreme. On the surface, that sounds useful. The crew gets to cover enormous distances without living through the entire journey subjectively. But think about what it actually requires. Getting to 99% of light speed means accelerating a spacecraft, plus crew, plus supplies, plus any shielding, plus any equipment, to within 1% of the fastest anything can travel. The energy requirement for that is not 10 times what we currently produce. It's not 1,000 times. It's many orders of magnitude beyond the total energy output of human civilization. Every power plant, every solar panel, every fuel source on Earth combined, running for years, couldn't get you there. We're talking about energy budgets that belong to stars, not civilizations. And here's the part people don't think about enough. Even if you could somehow hit 90% of light speed, you still have to decelerate when you get there. Whatever destination you're heading toward, you can't arrive at 90% of light speed and do anything useful. You'd scream past it in seconds. Slowing down requires just as much energy as speeding up, so the energy problem doubles, at minimum. Now let's talk about the Oort Cloud specifically, because this is where the speed of light stops being an abstract physics problem and becomes a direct statement about our solar system. The Oort Cloud is estimated to extend somewhere between 2,000 and 100,000 AU from the Sun. At its outer edge, that's roughly 1 to 2 light-years thick, not 1 to 2 light-years away. 1 to 2 light-years of material you'd have to pass through just to clear our own solar system. Light itself takes 1 to 2 years to cross the Oort Cloud. Light. The fastest thing in the universe takes years. Any spacecraft we build, any spacecraft we could ever theoretically build, travels slower than light, which means the Oort Cloud alone represents a journey of many years at absolute best, and thousands of years with anything we currently have or are close to developing. You don't even reach the boundary of the solar system before the speed of light limitation has already cost you years. Here's the uncomfortable truth that all of this builds toward. The speed of light was never designed with us in mind. The universe has a speed limit, and that speed limit makes the solar system effectively impassable for anything with mass on any timescale that resembles human experience. You can't legislate your way around it. You can't fund your way around it. There's no discovery waiting in a laboratory that removes this constraint, because it's not a constraint of our ignorance. It's a constraint of reality itself. Some physicists have speculated about exotic workarounds, warp drives that compress space in front of a spacecraft and expand it behind, wormholes that create shortcuts through space-time. These concepts exist within theoretical physics. They're not fantasies exactly, but they require forms of matter and energy that may not exist. At scales of manipulation we have no framework for achieving. Even the most generous assessment of those ideas puts them beyond any civilization we can reasonably picture humans becoming, and most physicists consider them deeply unlikely. What we're left with is this. We live in a universe where distances between stars are measured in light years. We live on a planet in a solar system whose outer boundary is measured in light years, and the fastest we can ever travel is a fraction of what it takes to cross those distances in any time frame that matters. The math doesn't leave a gap. It closes the door. The speed of light isn't a challenge we haven't solved yet. It's the universe telling us, in the clearest possible terms, where the limit is. Let's say you somehow solved the propulsion problem and you're actually accelerating to a meaningful fraction of light speed. You've cracked the fuel equation. The engine works. You're building velocity in a way no human spacecraft has ever managed. And here's where the universe introduces a whole new category of problem that most people never think about. Going fast isn't just hard to achieve. It turns out that going fast is also trying to kill you in ways that have nothing to do with your engine. Let's start with the debris problem, because this one is genuinely terrifying. Interstellar space looks empty. On any map you've ever seen, it's just blank, a void between the stars. But it isn't actually empty. There are hydrogen atoms out there, floating in the darkness at a density of roughly 1.8 atoms per cubic centimeter. There's also the occasional grain of dust, the occasional speck of rock. At the speeds you're used to thinking about, none of that matters at all. A grain of sand hitting a spacecraft at normal orbital velocities is a non-event. At 10% the speed of light, that same grain of sand hits your spacecraft with the kinetic energy of several kilograms of TNT. Think about that for a second. A particle you can barely see. TNT-level detonation. A pebble, something you'd kick out of your shoe without a second thought, carries the energy of a nuclear weapon at those velocities. And you can't see them coming. You can't steer around them. They're just there, in the dark, waiting for you to hit them at 18,600 miles per second. Now here's where it gets worse. The hydrogen itself becomes the threat. At relativistic speeds, those sparse hydrogen atoms aren't just bumping gently against your hull. From your ship's frame of reference, they're slamming into you like a particle accelerator beam. The proton flux your spacecraft would encounter at a significant fraction of light speed would produce radiation levels that are lethal almost immediately. Not over decades, not over years, almost immediately. Your shielding, whatever you've built, however thick, however dense, would need to stop the entire interstellar medium from interacting with your ship at relativistic energies. That's not an engineering problem with an engineering solution. You can't build a wall against physics. The medium is everywhere. You're moving through it at a fraction of light speed. The interaction is unavoidable, and the result is catastrophic. There's a concept physicists call the interstellar medium radiation problem, and it's one of the quieter nightmares of relativistic travel theory. Researchers have actually run the numbers on what a ship moving at 20% light speed, the speed Breakthrough Starshot is hoping to push its tiny probe, would experience passing through even the thinnest regions of interstellar space. The radiation dose to any biological material on board would be extreme. Electronics would degrade rapidly. The very act of moving fast enough to make the journey worthwhile makes the journey unsurvivable for the thing you're trying to get there. Here's another problem nobody talks about enough: navigation. You're hurtling through space at a fraction of light speed, and you need to know where you are. Simple enough, right? Except that at relativistic velocities, the light coming from the stars around you is Doppler shifted. Stars directly ahead of you blue shift. They appear at higher frequencies, shifted toward ultraviolet and beyond. Stars behind you redshift. The faster you go, the more dramatic this distortion becomes. The star field you see out your window doesn't match any chart you brought with you. Your reference points are warped by your own velocity, and the faster you go, the worse it gets. At high fractions of light speed, the entire visible universe appears to compress into a bright disk ahead of you, with almost nothing visible to the sides or behind. Your star charts are useless. Your navigation instruments, calibrated for the universe at rest, are reading a universe that looks completely different from inside your moving frame. Course corrections require burning fuel you can't afford to burn. Every adjustment costs you range, and adjustments become increasingly difficult when you can't reliably determine your position in the first place. Then there are the structural stresses. Getting to 10% light speed isn't instantaneous. You have to accelerate. And to make the journey feasible in a human lifetime, you'd need to sustain meaningful acceleration for extended periods. The forces involved in accelerating a large spacecraft with enough mass to protect its crew, carry its systems, and store its fuel are enormous. Materials science has limits. Structural integrity has limits. The same spacecraft that needs to be light enough to actually reach relativistic speeds needs to be strong enough to withstand the stresses of sustained acceleration and eventually deceleration. Those two requirements fight each other at every design stage. You build lighter and the structure fails. You build stronger and you can't accelerate. And deceleration is its own catastrophe. Getting up to speed is only half the problem. If you actually want to stop at your destination rather than fly through it at 18,000 miles per second, you need to slow down. That requires the same fuel expenditure as speeding up, which means you need twice the fuel, which means the mass ratio problem that already seemed impossible doubles. Most theoretical relativistic mission concepts quietly drop the deceleration requirement. They plan for a flyby, not an arrival. You scream past the destination, take your measurements in the few hours you're close enough to observe anything, and keep going forever. The irony threading through all of this is hard to miss. The faster you go, the more the universe pushes back. The interstellar medium becomes a radiation bath. Dust becomes a weapon. Your star charts stop working. Your structure fights itself. Speed, it turns out, doesn't just make the journey shorter. It makes the journey itself increasingly hostile to the thing doing the traveling. There's a reason the International Space Station stays in low Earth orbit, well inside the protection of Earth's magnetic field. And it's not just because going farther is expensive. It's because space is trying to kill you, not metaphorically, literally. The moment you leave the protective bubble that Earth's magnetic field and atmosphere create, you are exposed to one of the most hostile radiation environments imaginable. And most people have no idea how severe that problem actually is. Let's start with what radiation in space actually means, because it's not the same thing as the X-ray you get at the dentist. Cosmic rays are high-energy particles, protons, helium nuclei, heavier atomic nuclei, accelerated to near-light speeds by some of the most violent events in the universe. Supernovae, black holes consuming matter, collisions between neutron stars. These particles travel across the galaxy for millions of years and hit your spacecraft at energies that dwarf anything produced in a laboratory. When they pass through a human body, they don't just bounce off. They smash through DNA strands, damage cell membranes, and cause cascading biological effects that build up over time. The damage is cumulative. There's no recovering between doses the way you might recover from a sunburn. Here's what that actually looks like in numbers. Astronauts on the International Space Station receive roughly 150 to 200 millisieverts of radiation per year. The safe annual dose limit for radiation workers on Earth is about 50 millisieverts. So astronauts on the ISS, inside Earth's magnetic field, with significant shielding, are already getting 3 to 4 times what we consider an acceptable occupational exposure. After 6 months on the ISS, the lifetime cancer risk for a crew member has gone up by a measurable percentage. That's 6 months in low Earth orbit, still protected by Earth's magnetosphere. Now take away that protection entirely. Beyond the heliopause, where the Voyager probes now travel, the radiation environment is dramatically worse. There's no solar wind to deflect incoming cosmic rays. There's no planetary magnetic field. There's nothing between you and the full, unfiltered output of the galaxy's most violent processes. Radiation doses in interstellar space are estimated to be several times higher than what the ISS crew experiences. For a crew traveling toward the Oort Cloud over years or decades, the cumulative exposure wouldn't just raise cancer risk, it would be genuinely catastrophic. DNA damage at that scale begins to overwhelm the body's repair mechanisms. Neurological effects, memory problems, cognitive decline have been documented in astronauts on relatively short missions. Extend that timeline to decades, and you're not looking at elevated cancer risk. You're looking at a crew that's being slowly destroyed by the environment they're traveling through. The obvious answer is shielding. Build thick walls. Put enough material between the crew and the incoming radiation. But this is where the problem loops back into everything we talked about earlier. Shielding adds mass. Mass requires more fuel to accelerate. More fuel means a heavier spacecraft, which means you need even more fuel. And here's the brutal part. The shielding that would actually stop the most energetic cosmic ray particles, the ones with the highest energy, the ones that punch through almost anything, doesn't really exist in a practical form. Some cosmic rays carry energies so extreme that passing through meters of solid lead would barely slow them down. The particles that do the worst biological damage are precisely the particles that are hardest to stop. You can build shielding that blocks the lower energy radiation and provides real protection against solar particle events, which are dangerous bursts of radiation from the sun. But the galactic cosmic rays, the truly high-energy stuff, will get through. Think about that. There's another layer to this. It's not just the radiation passing through people. It's the radiation passing through electronics, the computers, the life support systems, the navigation equipment. All of it is vulnerable to cosmic ray damage. High-energy particles can flip bits in computer memory, corrupt data, and cause hardware failures. On Earth, electronics are shielded by the planet itself. In deep space, radiation hardening is required, which means heavier, bulkier, more expensive components with lower processing power than their consumer equivalents. The Voyager probes are experiencing this right now. Decades of cosmic ray exposure have contributed to the degradation of their onboard systems, and engineers have had to perform increasingly creative workarounds to keep them functioning. Voyager 1 is 47 years old and losing the battle slowly. Human crew members don. It get to be reprogrammed remotely. And the farther you go from the sun, the worse it gets. Inside the heliosphere, the solar wind provides some protection. It deflects and scatters incoming cosmic rays, reducing the dose. This is called the heliospheric modulation of cosmic rays, and it's a real effect. Cosmic ray intensity inside the heliosphere is actually lower than in interstellar space because of it. When Voyager 1 crossed the heliopause in 2012, instruments recorded a sharp increase in cosmic ray intensity almost immediately. Interstellar space is measurably significantly more radioactive than the outer solar system. A spacecraft heading for the Oort Cloud and beyond isn't moving toward a safer environment. It's moving toward a worse one every single day. The math for a crewed mission doesn't work. Not with any shielding technology we have or any that's currently on the drawing board. A multi-decade journey through the outer solar system and into interstellar space would expose the crew to radiation doses that would be lethal on any meaningful timeline. This isn't a problem we're close to solving. It's a problem we don't have a credible path toward solving. And in the meantime, the Voyager probes drift outward through exactly this environment, their instruments slowly degrading, their signals growing weaker, a preview of what any spacecraft faces in the deep dark beyond the sun's protection. Space isn't just empty, it's full of something invisible, and that something would be killing you the entire time. We've been talking about the engineering and the physics, but there's another problem that's just as fundamental, and it lives inside the people we'd be sending. The human body is not built for space. That sounds obvious when you say it out loud, but most people don't fully appreciate what that actually means when you start stretching the timeline from weeks to months to years. Radiation is the threat that comes from outside the spacecraft. This one comes from within. The moment you leave Earth's gravity behind, your body begins dismantling itself in ways that are quiet, relentless, and surprisingly hard to stop. Start with bone loss. In microgravity, your skeleton has no load to carry. It doesn't need to support your weight because nothing has weight anymore. So your body, being the efficient biological machine that it is, stops investing in maintaining bone density. You lose roughly 1 to 2% of your bone mass every single month in space. That's not a typo. 1 to 2% per month. Osteoporosis in elderly adults on Earth progresses at around 1% per year. Astronauts experience that rate compressed into a single month, over and over again for as long as they're up there. On a mission measured in decades, the math becomes grotesque. You could arrive at your destination barely able to stand, assuming you could stand at all. Muscles followed the same logic. Without gravity to push against, they atrophy. Your legs become nearly useless. Your core weakens. Astronauts returning from 6-month stays on the International Space Station often can't walk unassisted when they land. They have to be carried out of the capsule. Their bodies need months of rehabilitation just to recover from half a year in orbit. Now imagine 10 years, 20 years, 40 years. Think about that for a second. Then there's what happens to the fluid in your body. On Earth, gravity pulls blood and fluid downward toward your lower extremities. In microgravity, that mechanism disappears and fluid migrates toward the upper body and the head. This creates chronic pressure on the optic nerve. A significant number of astronauts who have spent extended time on the space station come back with measurably altered vision. Some experience permanent changes to the structure of their eyeballs. The condition even has a name now: spaceflight-associated neuroocular syndrome. We don't fully understand it yet. We definitely don't have a reliable fix. The immune system degrades. Latent viruses that your body normally suppresses, herpes strains, varicella, others, begin to reactivate. The immune system, already stressed by radiation and sleep disruption and psychological pressure, struggles to keep them in check. Blood pressure regulation becomes erratic. Cardiovascular deconditioning begins almost immediately after arrival in microgravity, as the heart no longer has to work as hard to pump blood against gravity's pull. It weakens. Its shape actually changes over extended missions. Here's what makes all of this particularly uncomfortable. The longest any human being has ever spent continuously in space is around 14 months. That was Valery Polyakov aboard the Russian Mir station in the 1990s. Mark Vande Hey spent just over a year on the ISS more recently. Those are the outer edges of our data. Everything beyond that is extrapolation, and the extrapolations are not encouraging. We genuinely don't know what happens to the human body over 5 years in space, let alone 20 or 30. The trajectory of deterioration suggests it gets worse, not better. Astronauts on the space station exercise for roughly 2 hours every single day specifically to fight this deterioration. 2 hours of intense physical training daily just to slow the damage. Not stop it, slow it. And they're doing this while orbiting at only 250 miles above Earth, well inside the radiation protection of the magnetosphere, with regular resupply missions arriving every few months and a return vehicle always docked and ready. The infrastructure supporting them is enormous. On a deep space mission to the outer solar system, none of that exists. No resupply, no return vehicle, no real-time communication with doctors on the ground. Just the crew and whatever medical knowledge and equipment they launched with. One proposed solution to the microgravity problem is artificial gravity through rotation. If you spin a spacecraft, centrifugal force mimics gravity. This is theoretically sound. The problem is the engineering. To create a rotation that feels like gravity without causing debilitating Coriolis effects. The sensation of moving differently depending on which direction you turn your head. The rotating structure needs to be at least 100 meters in radius, probably more. That is an enormous structure to build, launch, and maintain. It adds mass. Mass requires fuel. Fuel requires more mass. And it introduces mechanical complexity that over decades of operation creates new failure points. Something that has to spin continuously for 40 years will eventually fail. Everything does. And even artificial gravity only addresses one piece of this. It doesn't fix the radiation damage building up in crew members' cells. It doesn't resolve immune dysfunction. It doesn't protect vision. It doesn't restore the biological rhythms that space travel disrupts. You'd still be sending human beings into an environment they were never designed to survive in, for timescales that have no precedent in the history of human spaceflight, with no safety net whatsoever. The engineers can build better rockets. They can design better shielding. They can devise more efficient propulsion systems, but they cannot redesign the human body. That body evolved over millions of years on the surface of one particular planet, tuned by natural selection to operate in a very specific gravitational field, atmosphere, radiation environment, and biological ecosystem. Remove it from all of that, and it begins to fail, slowly at first, then faster. There's no patch for that. There's no technology upgrade. The human body isn't a machine we can modify to tolerate space. It's a product of 4 billion years of evolution on one specific planet, and it shows. Put everything we've talked about together, and you arrive at a problem that isn't really about propulsion, or radiation, or engineering at all. It's about time, and time is the one thing we cannot engineer our way out of. Let's do the math, because the numbers here are genuinely uncomfortable. The best propulsion concept we can actually imagine building, not chemical rockets, not ion drives, but a hypothetical fusion or nuclear system, might get a spacecraft to around 10% the speed of light. That's roughly 67 million miles per hour. It's 40 times faster than anything we've ever launched. It would be the most extraordinary engineering achievement in human history. And at that speed, the journey to Proxima Centauri takes about 42 years one way. Not a weekend trip, not a mission rotation. 42 years of continuous travel just to arrive. Think about that for a second. The psychological reality, though, goes far deeper than simple mathematics or engineering. You're leaving everything familiar behind, not for a distant shore you might glimpse someday, but for an abstract point in space you will never actually see again. The loved ones you leave will age and die while you're still en route. You cannot visit them during brief stops. You cannot return for emergencies or goodbyes. You cannot change your mind halfway through. This is the human cost underlying any serious discussion of true interstellar space travel. Depart at age 30, and you'd be 72 upon arrival. You'd spend your entire working life, your prime years, your middle age, all of it, sitting inside a spacecraft, watching the stars barely move. And that's a one-way trip. A round trip at 10% light speed to the nearest star and back takes roughly 85 years. You'd have to launch at birth and return at death, assuming perfect conditions, zero deceleration time, and not a single moment to actually look around when you got there. That's not a mission. That's a life sentence measured in light years. But here's where it gets worse. We've been talking about Proxima Centauri as the destination. That's the nearest star to our sun. And before you even get there, you still have to get out of the solar system. That means crossing the Oort Cloud. The inner edge of the Oort cloud starts at roughly 2000 AU from the Sun. At 10% light speed, you'd reach it in a few weeks. That part isn't the problem. The problem is that the Oort cloud doesn't end there. It extends outward to somewhere between 100,000 and 200,000 AU. That's roughly 2 light-years of distance in every direction, filled with icy debris still gravitationally bound to the Sun. Passing through it completely, at 10% light speed, would take decades. Not years, decades. Just across the outer boundary of our own solar system. And then you'd still have another 2+ light-years of actual interstellar space before you reached the nearest star. The Oort cloud alone is a multi-generational problem. No crewed mission in the history of spaceflight has lasted longer than about 14 months. The record is held by a Russian cosmonaut who spent 437 consecutive days aboard the Mir space station. That's our benchmark. That's the furthest we've pushed a human body in space under controlled conditions. We're talking about missions that would need to last not months, not years, but centuries to reach the true edge of the solar system. Let's say we solve every biological problem. Let's say we build rotating sections for artificial gravity, perfect radiation shielding, closed-loop life support that recycles everything without failure for 200 years. Even then, the people who launched would not be the people who arrived. Their children wouldn't arrive. Their grandchildren wouldn't arrive. You're looking at 5 or 6 generations of humans born, raised, and dying aboard a spacecraft with no choice in the matter before the mission reaches the edge of the solar system. That isn't exploration. That's something else entirely. And there's another layer to this that people don't usually confront directly. Even at 10% light speed, you're still only at 10% light speed. You're not relativistic enough for time dilation to meaningfully compress the journey. At that velocity, the crew ages at roughly the same rate as people back on Earth. The clocks aren't running differently. The years are real years, experienced in full, one after another. There's no shortcut through physics at these speeds. Time dilation becomes significant only when you're approaching a large fraction of light speed, 50%, 80%, 90%, and getting to those velocities with any payload worth sending requires energy we cannot conceive of producing. So you can't go slow enough to use existing technology, and you can't go fast enough to use time dilation as a workaround. You're stuck in the middle, where the distances are vast and the years are real, and the human lifespan is what it's always been, about 80 years if you're lucky. There are stars in our galaxy that are 10,000 light-years away. Even at light speed itself, a round trip takes 20,000 years. The entire span of recorded human civilization is 5,000 years. Our fastest probe, Voyager 1, launched 47 years ago and will spend the next 30,000 years just crossing the Oort cloud. These aren't numbers that suggest a gap in technology. They suggest a fundamental mismatch between the scale of the universe and the scale of a human life. We measure our lives in decades. We measure this problem in millennia. And that gap doesn't close with a better rocket. It doesn't close with a more efficient engine, or a more determined crew, or a larger budget. The Oort cloud is 2 light-years thick. Proxima Centauri is 4.24 light-years away. Human beings live for roughly 80 years. These are fixed quantities. You cannot negotiate with them. The solar system is simply larger than a human life, And that might be the most honest way to say what we're really up against. Let's say we build the ship, we solve the propulsion, we find a way to handle the radiation. We still haven't solved for the most unpredictable part of any crewed mission: the human mind. We know what happens when you put people in isolated, confined environments for extended periods. We've studied it extensively. Antarctic research stations, submarine crews, cosmonauts on the ISS. The pattern is always the same. There's an early phase where everything feels meaningful and exciting. The mission matters, the crew is bonded, everyone is performing at their best. That phase ends, and what replaces it is something researchers have documented so consistently it has its own name: the third quarter phenomenon. Roughly 3/4 of the way through a long, isolated mission, morale collapses, conflict spikes, depression sets in. The same faces that felt like teammates start feeling like cellmates. Now compress that experience into a spacecraft that's been traveling for 20 years, with no end in sight and no way out. On Earth, when things get unbearable, you can leave. You quit the job. You drive away. You call someone. That option doesn't exist on an interstellar mission. There's no hatch you can open, no emergency extraction, no one coming to help. You are locked inside a metal container with the same 8 or 12 people, breathing recycled air, walking the same corridors, hearing the same machinery for decades. The psychological weight of that is something we genuinely don't know how to manage, and we've never had to manage it for anything close to the timescales we're talking about. The longest continuous spaceflight in history was just over 437 days. The mission to the Oort Cloud's inner edge would take centuries. The gap between those two numbers isn't a gap we bridge with better crew selection or more thorough psychological screening. It's a completely different category of problem. Communication makes it worse. A lot worse. On the ISS, astronauts can call their families. There's a delay of milliseconds. They can watch live television. They can have a real conversation. On a mission heading deep into the solar system, the communication delay grows with every passing year. At the inner edge of the Oort Cloud, a signal takes months to arrive. A message sent home and a reply received spans close to a year, minimum. Further out, it's years. You send a message saying your crewmate is having a breakdown and you don't know what to do. Mission Control responds. You receive that response years later. Whatever was happening then has either resolved itself or destroyed the crew. There is no real-time support. You are functionally alone in a way no human being has ever experienced. Think about what that means for mental health crises, for conflict, for grief. Someone on the crew loses a parent. The message arrives years after the death occurred. The funeral happened. The family mourned and moved on. And now this person is processing that loss inside a sealed spacecraft with nowhere to go and no one outside who can reach them. There's no framework for that. No therapy protocol. No grief counselor. Nothing we've ever built or trained for comes close to preparing someone for that experience. Governance is a problem nobody likes to talk about, and it's terrifying. Who's in charge? A military-style command structure sounds clean in theory. In practice, after 20 years of confinement, authority becomes deeply complicated. What happens when the commander makes a decision the crew believes is wrong? There's no appeals process, no higher authority, no way to remove someone from power. What happens when someone on the crew becomes genuinely dangerous? There are no police, no brig that works long-term, no way to separate someone from the group in any meaningful sense. On Earth, we have thousands of years of developed legal and social infrastructure for handling conflict. On this spacecraft, you have none of it. You have a crew manual and each other. Children born on the ship didn't consent to any of it. That dimension of a multi-generational mission is one that almost never gets addressed honestly. If a journey takes longer than one human lifetime, and escaping the solar system almost certainly does, then the people who complete it aren't the people who started it. The second generation, the third, they were born into a mission they had no say in. Their entire world is a corridor. Their entire sky is a bulkhead. They've never felt wind. They've never seen a horizon. What does that do to a person? We don't know. We've never done it. And the ethical questions around engineering a society of people who have no choice but to continue a voyage they didn't choose are ones that don't have comfortable answers. The crew that sets out would also have to make peace with something most of us spend our whole lives avoiding thinking about. The people they love are back on Earth, aging. By the time a decade has passed, parents are gone. Friends have grown old. The world they left has changed in ways they'll never fully understand because the information arrives late and fragmented. You're not just leaving Earth, you're leaving your entire life. Every relationship, every familiar thing, every comfort, permanently. And you're doing it inside a vehicle the size of a building with the same small group of people for the rest of your existence. We don't have a psychological architecture that works for this. The closest models we have, submarine crews, Antarctic wintering teams, the ISS, all of them have defined endpoints. The crew knows when it's over. That endpoint is one of the most psychologically important anchors a person can have. Remove it, or stretch it to decades, and the psychological calculus changes completely. The mission stops feeling like a mission and starts feeling like existence itself. And humans are not well equipped to find meaning in an existence with no foreseeable change. You can shield a spacecraft from cosmic rays. Shielding the people inside from themselves is a different problem entirely, and we don't have a solution. All of this assumes someone is willing to pay for it, and that's an assumption worth examining very carefully, because we've spent a lot of time on the physics, the distances, the propulsion limits, the radiation, the rocket equation, the human body breaking down in ways we can't fully fix. All of that is real, and all of it is genuinely terrifying. But underneath every single one of those problems sits a more uncomfortable question. Who is actually going to fund this? And the honest answer, when you look at how human civilization actually works, is deeply unsettling. Let's start with the International Space Station. That project cost roughly $150 billion. It took 5 major space agencies, decades of sustained political cooperation, and an extraordinary alignment of Cold War-era ambitions that no longer exist in quite the same form. And the ISS sits 250 miles above Earth. It's the most expensive structure humanity has ever built, and it barely leaves the neighborhood. Now consider what it would take to build, launch, and sustain a mission aimed at the edge of the solar system. Not another star, not even close to another star. Just the outer boundary of the structure we're already sitting inside. The cost estimates for concepts like Project Orion or a fusion-powered spacecraft run into the tens of trillions of dollars. Some projections go higher. That's not 150 billion. That's 100 times more at minimum. And those figures assume everything goes according to plan, which nothing in the history of large-scale engineering ever does. Here's where things get uncomfortable. Governments don't think on those timescales. They think in 4-year cycles, election years, budget negotiations, approval ratings. A politician who votes to fund an interstellar mission won't live to see the first major milestone. Their children won't. Their grandchildren might not. There is no political incentive structure on Earth that rewards that kind of commitment, because the reward, if it ever comes, arrives long after everyone who made the decision is gone. Democratic governments are genuinely terrible at this class of problem. That's not a criticism of democracy, it's just an honest assessment of how the incentive structure works. Voters want results they can see. Schools, roads, hospitals. Not a spacecraft that won't reach the Oort Cloud for 300 years. So what about corporations? Private industry has driven incredible innovation in the last 2 decades. SpaceX did what NASA couldn't or wouldn't do on the same budget. Elon Musk talks about making humanity multiplanetary. Jeff Bezos founded Blue Origin with the explicit goal of moving heavy industry off Earth. These are serious people with serious resources. But even the most optimistic estimates of their personal wealth combined don't come close to the price tag of an actual solar system escape mission. Musk is worth somewhere around $200 to $300 billion, depending on the day. That sounds enormous. It's a fraction of what this would cost. And corporations, even the visionary ones, answer to returns. Revenue, profitability on some horizon that humans can actually live to see. There is no business model for escaping the solar system. You can't sell the Oort Cloud. You can't mine it, at least not in any time frame that produces a return. You can't charge passengers for a one-way journey that takes 1,000 years. The economic logic simply doesn't exist. International cooperation is the obvious answer, and it's also the most fragile one. The only way to mobilize resources on this scale is to pool them across nations. But look at the history. The ISS partnership has survived, but barely, through multiple geopolitical crises. The relationship between the United States and Russia in space has fractured and reformed more than once. China is building its own stations separately. These are not organizations that reliably cooperate across decades, much less across centuries. A mission to escape the solar system requires continuous, sustained collaboration across generations of leadership, across shifts in ideology, across wars and economic collapses and revolutions that we cannot predict. The political architecture required for that doesn't exist. It has never existed. And there's no particular reason to believe humanity is capable of building it. Then there's the question of what you're actually getting back. Every major scientific and exploratory mission in history has had some justification beyond pure curiosity. The Apollo program was partly geopolitical. The space shuttle developed commercial satellite deployment. Mars missions are framed around the possibility of life, resources, and a backup for civilization. What's the return on a solar system escape mission? Data? Maybe. Scientific knowledge? Certainly. The knowledge that we can do it. But none of that feeds anyone. None of it delivers clean water. None of it arrives in time to address any crisis that's actually happening on Earth right now, which is the competing priority that never goes away. And this is where the political debate gets brutal, Because the argument against spending trillions on the edge of our own solar system is not an irrational one. There are roughly 2 billion people on Earth without reliable access to clean drinking water. Hundreds of millions face food insecurity. The climate is changing in ways that will reshape where humanity can actually live within this century. These are urgent, present problems. The political will required to divert resources of this magnitude toward a project with no near-term return, whose benefits arrive in timescales measured in centuries, while those problems remain unsolved. That will is essentially impossible to generate and sustain, not because people are selfish or short-sighted, but because the math of human need in the project is simply more compelling than the math of human ambition in the abstract future. What this means practically is that the economic and political barriers to escaping the solar system may be harder than the physical ones. The physics, at least, is knowable. You can calculate what it would cost in energy. You can model what the rocket equation demands. Those are fixed quantities. The problem of building and sustaining sufficient political will across generations, across nations, across competing human crises, that has no fixed solution. It depends on human behavior, which is the most unpredictable variable of all. The money problem and the will problem might be harder to solve than the physics problem, and unlike the physics problem, they don't get easier with time. So let's ask the question the title promised we'd answer. Are we trapped? Not in the sense that something is holding us here against our will. No cage, no lock, no force actively preventing us from leaving. But trapped in a more uncomfortable way. Trapped by the convergence of everything we've spent the last hour walking through. The distances are too vast. The energy requirements are beyond anything we can realistically build. The human body breaks down. The human lifespan runs out. The political will evaporates. No single one of those things kills the dream on its own. Together they form something that functions exactly like a wall, even if no one built it to keep us in. Here's the thing that should unsettle you. The universe doesn't care about our ambitions. That's not pessimism. That's just accurate. The laws of physics were not written with human convenience in mind. Nobody looked at the scale of the solar system and said, let's make sure the species on the third planet can eventually get out. The distances are what they are. The speed of light is what it is. The rocket equation does what it does. These aren't problems waiting for a clever enough solution. They're the structure of reality. And when you line them all up and look at them honestly, the picture is uncomfortable. Think about the Fermi paradox for a second. The galaxy is roughly 100,000 light-years across. It's about 13 billion years old. There are hundreds of billions of stars in it, and we now know most of them have planets. The math suggests there should be other intelligent civilizations out there, maybe many of them, some far older than us. So where are they? Why is the galaxy apparently silent? One answer, and it's a grim one, is that escaping a home solar system is simply harder than we assume. Maybe every civilization that has ever existed eventually hits these same walls. Maybe the energy requirements, the timescales, the biological fragility, maybe these aren't unique to us. Maybe they're universal. Maybe we're not a young species with everything ahead of us. Maybe we're typical, stuck in our corner of the galaxy, able to measure the distances, unable to cross them. That's the uncomfortable version, and it deserves to be taken seriously. But here's where it gets genuinely complicated. About 200 years ago, serious scientists, not uninformed people, but educated, intelligent people, considered heavier-than-air flight to be essentially impossible. Lord Kelvin, one of the most respected physicists of the 19th century, said it. The mathematics, as they understood them, didn't support the idea of a machine heavier than air staying aloft through its own power. They were wrong. 100 years ago, reaching the moon was science fiction in the most literal sense. Stories written for entertainment, not engineering proposals. 40 years after those stories, a human being stood on the lunar surface and called home. The walls are real, but walls have fallen before. So which is it? Are we genuinely trapped, or are we just early? The honest answer is that we don't know, and that uncertainty is not comfortable to sit with when the stakes are this large. What we do know is that nothing in the current scientific understanding of physics points toward a breakthrough that would make solar system escape practical on any human timescale. There is no theoretical loophole waiting to be discovered that makes the Oort Cloud smaller, or human lifespans longer, or fuel requirements lower. Warp drives exist in mathematics on paper, barely, requiring exotic matter that may not exist, and energy densities we cannot approach. Wormholes require the same. These aren't engineering challenges with known paths forward. They're speculative structures built on speculative physics. And even if something does change, even if some discovery shifts what we think is possible, the timeline for that discovery arriving, being understood, being engineered into practical technology, and being deployed at the scale needed to cross the solar system runs into decades or centuries at minimum. The gap between where we are and where we'd need to be is not a year or a generation. It is civilizational. It requires sustained effort across timescales that no human institution has ever maintained. Now multiply that against what we talked about before this: the funding problem, the political will problem, the return on investment problem. Every decade that passes, the question gets asked again. Why this, when there are problems here on Earth demanding that money? And every decade, that question gets harder to answer in a way that moves governments and populations to act. The physics problem and the human problem are not separate. They reinforce each other. So here's where we land. Probably not. That's the honest answer to whether we will escape the solar system on any timescale that resembles a functioning human civilization. Probably not, and possibly not ever. Not because we're not trying, not because we're not clever enough, but because the universe didn't leave a door open just because something inside it developed the curiosity to look for one. That's grim. It should feel that way. The solar system is not a waiting room. For all practical purposes, for all of recorded history and for all of the history that is likely to follow, this is it. What you do with that fact is up to you. Some people find it motivating. Some find it crushing. Both reactions make sense. The scale of what's in front of us is real, and it doesn't shrink just because we prefer it to. And maybe the most honest thing we can say, after everything, is that the universe is under no obligation to be escapable, and the evidence suggests it isn't. Tonight we've looked at the distances, the physics, the propulsion problems, the biology, the psychology, the economics, and the philosophy of what it would really take to escape the solar system. And what you're left with, after all of that, is something that's genuinely hard to sit with. We live on a rock, a small one, orbiting one star out of hundreds of billions in this galaxy alone. And in the nearly 5 billion years this planet has existed, And in the roughly 300,000 years our species has walked around on it, we have never truly left the solar system. Not once. Not even close. That's not a failure of ambition. It's not a failure of intelligence, or courage, or engineering. The Voyager probes are proof of that. 2 spacecraft launched almost 50 years ago, representing some of the most careful and brilliant mission planning in human history, are still out there right now. Still moving, still transmitting, barely. Carrying golden records, with greetings in 55 languages, music, the sounds of rain and wind, and a mother's first words to her child. Those records were meant for anyone who might find them, and those probes will drift through the outer reaches of this solar system for another 30,000 years before they're genuinely gone. That's our best shot at the stars. 2 spacecraft the size of small cars, slowly going cold in the dark. There's something in that fact that's worth holding for a moment, not rushing past it. We are a species that looked up at the sky, figured out what those lights were, calculated their distances, built machines capable of reaching them in some small way, and then watched those machines crawl across the void for half a century without escaping. We know exactly how trapped we are. That's the remarkable part, not the being trapped, the knowing. It can feel crushing, or it can feel humbling. It depends on how you hold it. Maybe the honest answer to the question in tonight's title is that we probably won't escape, not on any timescale that resembles a human civilization. Maybe not ever. But we keep trying to understand it. We keep sending things out into the dark with golden records on them, just in case. If tonight gave you something to think about, something that shifted how you see the size of this place we live in, take a second to like the video or subscribe to the channel. It genuinely helps us reach more people who want to think about these things seriously. We put a lot into every one of these, and your support makes it possible to keep going. Sleep well tonight, knowing that the solar system that has held us our entire existence is so vast, so ancient, and so indifferent to our ambitions, and that we keep looking toward the edge of it anyway.